Let's begin by visualizing the standard real number line. We are all familiar with specific irrational values, like the square root of 2 shown here. We know for a fact that this value is not rational, and yet, because the real line is complete, we know this value must exist precisely at this point. But how do we generalize this? What guarantees that any positive number has a unique nth root waiting to be found? This question brings us to our focus, the existence of nth roots of positive real numbers. For any positive real number x and any positive integer n, a solution exists. Specifically, it guarantees 2 things. First, uniqueness. There is only one positive real number, y, that fits this equation. Second, existence. This number y definitely can be found. We can write this unique solution using radical notation or fractional exponents. For the proof, we will exploit the least upper bound property of real numbers. Our goal is to find a positive y, such that y to the power of n equals x. Uniqueness is guaranteed because the function yi to the power n is strictly increasing. For existence, we construct a specific set E. We define E as the set of all positive t, whose nth power is less than x. Let's visualize this set on the number line. E contains all numbers from 0 up to the root we are looking for. We must prove 2 things. First, that E is not empty, and second, that E has an upper bound. By the least upper bound property, E must have a supremum. Call it y. Now we ask, is it the root we are looking for? If y to the power of n is less than x, we can find a slightly larger number, y plus h, that is still in E. But that contradicts y being an upper bound. If y to the power of n is greater than x, we can find a smaller number, y minus k, that is an upper bound. But that contradicts y being the least upper bound. Thus, y to the power of n must equal x. The root exists. We need to show that there is at least one number in our set, E. Recall that E is the set of positive numbers, t, where t to the power of n is less than x. Consider this specific value for t, x over 1 plus x. Since x is positive, this fraction is strictly between 0 and 1. For any number between 0 and 1, raising it to a power n makes it smaller or equal. Also, since we divide x by something larger than 1, t must be less than x. Putting it together, t to the power of n is less than or equal to t, and t is less than x. Thus, t to the power of n is less than x, which means t is in E. E is not empty. We have established that the set E is non-empty and bounded above. By the least upper bound property, the supremum of E exists. Let's call it y. We begin with this standard algebraic identity. Assuming A is positive and less than B, observe the terms in the second factor. Notice that since A is less than B, every term here is strictly less than b to the n minus 1. Replacing each of the n terms with bs to the n minus 1 yields this strict inequality. Assume that y to the n is strictly less than x. We choose a positive h smaller than 1, and smaller than this fraction. Applying our previous identity with a equals y and b equals y plus h, we get this inequality. Since h is less than 1, y plus h is less than y plus 1. This allows us to simplify the upper bound. Substituting our choice of h, the whole expression is less than x minus y to the n. Rearranging terms, we find that y plus h to the n is still less than x. This means y plus h is in E. But since it's greater than y, this contradicts that y is an upper bound of E. Now, assume that y to the n is strictly greater than x. We define a positive k using this fraction, which is less than y. Applying our identity with a equals y minus k and b equals y, we get this upper bound. Substituting our definition of k, this simplifies exactly to y to the n minus x. Rearranging terms, we see that y minus k to the n is strictly greater than x. This implies no element of E can be greater than y minus k. So, y minus k is an upper bound. But y minus k is smaller than y, contradicting that y is the least upper bound, since both inequality cases lead to contradictions. Y to the n must equal x.